All right, so this morning we provided, or we discussed in quite a bit of details, a complete framework that we could use in order to combine a Lagrangian representation of a particle phase with the underlying fluid equations in a way that it counted fully for the volume occupied by the particles, any type of phase change process, any type of momentum exchange. We did that with no particular, well, at least very few assumptions. The idea being that we would then remain, I guess we would go down to the point where we have to now model the various unclosed terms. So the framework that we derived this morning is in fact very close. It's more of a systematic treatment of Euler-Lagrange type of approaches than anything else, really. This is, if you neglect a few things left and right, you essentially go back to the code that we've been working with for a little while now. So putting everything inside this code would be, like I said multiple times now, it would probably require us to spend a full 2 weeks on this topic. So instead of doing that, we're going to wrap up essentially today and tomorrow morning our discussion on particle-laden flows, so that next week we can start talking about the other side of liquid gas of multiphase flows that we haven't really gotten to yet, which is interfacial tracking type of problems, situations where we have a liquid and a gas separated by a complex-shaped interface. So what remains for us to do that I thought was reasonably accessible in a tutorial-type framework was the handling of the collisions. So we already highlighted the fact that as soon as your Stokes number is no longer negligible, it's very likely that you're going to have to at least deal with collisions with walls, with boundary conditions to your fluid. But we'll see that this becomes important also. At least we've discussed about the fact that interparticle collisions become very quickly important as well. And we'll talk more about that tomorrow as well. So we'll talk about collisions for a little while. We'll talk about two methods, or essentially two methods, and then we'll talk about the practical implementation for the second of those methods. We'll essentially do or introduce two simplifications that will be very straightforward, but will enable us to do things quite a bit more efficiently. And then we'll start looking at the code. The first code that we'll look at will contain this second collision model applied to particles interacting with our cylinder in our von Neumann vortex street problem. And so you'll see this is going to be a little chunk of code, essentially one do loop that's not particularly exciting, that will contain an implementation of the equations we'll discuss right now. And we'll play with it a little bit, and then we'll start modifying that to do particle-particle interactions. Okay? Any questions before we start? All right. So the first approach to probably the most standard approach for collision modeling, either between particle pairs or particle and a surface, is the idea of what's called hard sphere collision. So we're going to distinguish between our two approaches as one being called hard sphere, the other one being called soft sphere. So one approach will essentially say that by all intents and purposes, if your particle is a solid material, its Young modulus is probably such that the collision will involve very little deformation, and as such the collision should be near instantaneous compared to the characteristic flow timescales. Okay? Because of this expected wide difference between the collisional timescale, the actual time it takes for the collision to take place, and the surrounding flow scales and the timescales we want to resolve in the flow, it makes a lot of sense to just say, well, let's just assume the collision is perfectly instantaneous. And what that means, if we go back to the world of contact mechanics, is if you have no time spent in the collision, that means that there's no time for deformation. So you're basically saying that your particle is going to be perfectly hard. There's going to be no deformation whatsoever. We know it's not true. We know that if you throw even a hard metal onto a solid surface of hard metal, there will be some small deformation that would lead to some energy dissipation during the collision process. So, fine, we'll reintroduce that. The way that's been classically looked at is from the perspective of simply setting up a set of equations in order to relate the outcome of the collision to the input into the collision. So basically imagine I have just one particle hitting a surface. So this is this configuration sketched down there. That particle will be characterized by velocity. Well, this is not comprehensive. Oh, I guess it reasonably is. So imagine I have a particle characterized by an angular velocity. I can assume for the sake of simplicity a single component, but really in general this would be a vector, as well as an incoming, right before the collision, a certain velocity vector. So I have linear velocity, angular velocity. What I'm interested in figuring out is what is after this collision has taken place. Now identify here with a little 2 superscript. The 2 will become maybe not obvious, but I'll explain why we put a 2. We're interested in knowing what's the outcome in terms of linear velocity and angular velocity. So if you talk to someone doing contact mechanics, they'll tell you that's not difficult. I can give you a model for this process. If you tell me what the surface is like, what the materials are, give me a Young's modulus, I'll estimate the dissipation. I'll estimate the ratio of the incoming energy to the departing energy of the particle. And, well, maybe we should start with some basic phenomenology, right? What would happen is if we had no friction whatsoever, the particle would undergo perfect specular reflection. There would be no rotation induced. We would just go down, bounce off at exactly minus the incoming angle. That would be an elastic collision. If you had now an inelastic collision, you would go back out at a lower angle and you would lose some of the kinetic energy of the particle. Now, if you account for friction, what's going to happen is that upon impact, the particle will start rotating. Okay? And so an impact, even if you have an incoming particle that has no angular velocity, will leave with both linear velocity but also angular velocity. Now, if you go one step beyond, what really happens is that depending on the conditions, the shallowness of the angle and the characteristics of the surface, you would expect that when the particle comes in, it might in fact first slide and then start rolling and then bounce off. So that's the phenomenology that people doing contact mechanics tell us. I don't do that. I'm fed this model by other people. If you're not happy with this, let me know. Give me better, better information about this. But don't blame me. Blame the people who feed me models. So that's the underlying phenomenology. But basically, if someone tells you this is the relation between the incoming conditions and the outgoing conditions, well, that's going to look like a big set of coupled equations like this. So in the general sense, we'll have the setup for the problem will be this. 6 equations. Three for the translational motion. And 3 for the rotational motion. And that's good news because there's really 6 unknowns from this process. We know everything about the incoming conditions. We suppose that we know everything about the materials. So the only thing we don't know is the outcoming velocity, both linear and angular. So we have 6 unknowns. Okay, and that again requires some sort of a contact model that might look like what I wrote below. That will typically contain some sort of a friction model plus some sort of a notion of a restitution coefficient, the ratio of energy out to energy in. This restitution coefficient, I'll already give it a name, we'll call it E. An elastic collision would be a restitution coefficient of 1, all right? So the idea of the hard sphere collision model is to say it is reasonable to approximate this process as being instantaneous, and so we'll mathematically translate that into an instantaneous solve of this. Oh, we have a, hooray. Okay, I did not notice that. So now is everything more visible, readable? Okay, good. So if you give yourself this set of 6 equations, you can just solve them, essentially. That's what we're saying. So I'll list the corresponding assumptions. Oh, I meant to include a reference. I'll have one. We'll touch back. I think I'll have a slide that will kind of connect back to that next week, and it will contain a reference if you're interested. Or we can talk about that. I can dig up a reference. So we'll assume that we're working with spheres here. Anything else will be a lot more complicated. Again, we're assuming that we have no deformation. Because we're assuming spheres without deformations, that means that we're assuming no roughness, or at least no roughness on the reference scale that cannot be modeled beyond just a Coulomb friction law or restitution coefficient. So there's no roughness here. What's written here is based on the Coulomb friction law, which essentially is a statement that you'll first slide. Once you stop sliding, you rotate. So once sliding on the surface stops, no further sliding can occur. So you slide until you've depleted enough energy, and then the particle starts rotating. The way you put together a model like that from the contact model is using usually impulse theory. So you're going to use the concept of instantaneous delta of momentum. You're basically saying that an instantaneous impulse will take you from your incoming velocity to rest at the surface of the wall, and then you're going to have a second what's called recovery impulse that will give you back your outward momentum. So the idea for formulating this is to use impulses. Impulse 1 is a compression impulse, even though there's no deformation. And it's essentially the impulse that will take a particle and stop it. So this is the first instantaneous event that stops the particle, and then you have a second event that moves the particle again. So that stops the particle. And number 2 is the recovery. And that rebounds, if you will, the particle. By the way, while I'm at it, so if you have those 2 impulses, we can, so classically we'll write this in the following form. This impulse you would write, so if you think of this in the vertical direction, in the wall normal direction, say call it y, this impulse will be the first impulse, and this impulse will be the second y impulse. And so the restitution coefficient will be the ratio between those 2 impulses, jy2 over jy1. Okay. Okay, so this is all fine. Now, in terms of the implementation, so it seems like this is practical from the perspective of the fact that collisions are instantaneous. They're handled. Once they happen, they are treated. The issue, though, is that there's the other side of this instantaneous collision is that you need to imply this impulse treatment exactly at the time of contact between two particles in a colliding pair. That means that if you look at your particle field at time t, you might not have any particles in direct contact. And then when you look at your particle field at times t plus delta t, you might still not have any particle in direct contact, but it could be that in between, two particles actually establish contact. Well, now that means that you're going to have to deal with likely collision pairs, identify them, and figure out exactly when it is that they would collide, at what time they would collide. And then you would apply a model like this. So, provided collisions are rare, this is fine. This is easy to do, right? You can easily look at your collision pairs. You look at your pairs of particles, and then you look at where they're heading. And then you look at whether their trajectory suggests that they will impact or not. And if the answer is yes, you can calculate exactly at what time it will happen. So it's not easy. It's not difficult doing that. It's fine. But now start thinking about, say, a configuration like this. Let me zoom in to have a bit more space. What would happen in a situation where you have... So what I said is that if you have a particle like this and a particle like this one moving this way and this one moving this way, it is easy to figure out that there exists a time where contact will happen. So this is this is at t, and this will be at t plus some delta t. You can identify that. Now, here's a different situation. What's going to happen if you have a particle here, a particle here, a particle here, and those two are moving like that? Well, you could argue still that this is reasonably easy to figure out. You can certainly look at the three current collision pairs and decide what's going to happen. But you can see already that it's not that obvious. You know, the question of whether those two particles are going to be hitting one another is significantly simpler to answer than the question, is that collision pair going to undergo collision first or not? Basically, if I show you this, it is not obvious for you to tell me whether this particle is going to collide with that particle first, or that particle is going to collide with that particle first, or if maybe those two particles are going to hit together right before. That's more tricky, and that requires a significantly finer time resolution of the process. If those two particles hit first, right, it might happen at t plus delta t, you would still have to figure out just after that at t plus delta t plus epsilon whether any of those two particles are then going to hit with that guy, or maybe both. So what you can see is that if I have more particles, it's significantly more complicated to already account for this in terms of temporally resolving when the collision happens. So I'll make a point here, maybe list questions. One question here is how to efficiently detect collisions especially for higher volume fraction. That is, the higher your collision frequency, the more often you undergo collisions, the more of this probing of when the collision really happened you're going to need to do. That's one problem. Let me ask you a second problem. So I'll recast first this first problem into maybe another perspective. That is essentially the complexity of the algorithm is going to increase rapidly with number of particles. That's essentially what it is. Complexity increases with NP. The second problem with this method, I'll just, well, let me, if you'll allow me, I'll go here to the side, and I'll just sketch a little configuration like this. A flat surface, gravity pointing down, as it tends to do, and a particle. Okay, flat surface and a particle perfectly at rest on top of that surface. So how do you model this with a hot sphere collision model? And the hot sphere collision model, we said we're building it upon the idea of instantaneous phenomena. We're doing impulses. Okay. So conceptually, it's not too complicated, right? You expose this guy to gravity, it falls. It goes in, you predict that there's a collision, you impose your impulse, you fix it. That happened at time 0. At time 0 plus epsilon, you let gravity do its thing, the particle move down, you detect that there's going to be a collision, you apply the impulse, and you repel the particle. That's 0 plus epsilon. Basically, you need an infinite number of impulses in order to sustain the simple situation of a particle sitting on the wall. That means that if you expect in any way sustained contact between particles, the hot sphere collision model is actually going to slow down to a crawl. Now we're going to have to basically spend all our time doing collisions just because we've decided to go after a distribution-based or an impulse-based representation of that process. So something like that you cannot do. So I'll just say it here, sustained contact is a problem. Okay. I'll make a simple observation here, which is that if your volume fraction, if you have interest in modeling collision in a system where the volume fraction is not that high, you're probably completely fine with hot sphere collisions. Probably completely fine. If you're maybe more on the end of chemical engineering and you're interested in gasification and vertical risers and maybe underwater slurry transports, you probably want to stay away from hot sphere collisions because those are systems where the particle phase is going to be dense. All right, any questions on this? Okay, so we've talked about the hot sphere collision model. We'll introduce oh, sorry, yes, go ahead.
The particles are rotating.
Yes.
And approaching each other.
Yes.
There is this normal direction collision. It collides like this way. But when it's sliding, there will be a slip in the tangential direction.
Yes.
So we are not accounting that.
We are here. We're just looking at one particle hitting a wall, right? This is the particle before collision, hitting the wall, and then departing. The way I put this together, this is just an example of particle and wall, but you can apply that to particle. Because we're solving for the full state of the particle after the collision, it is accounting for the slip and the rotation of the particle, so we're accounting for all this. It is. This is just a full impulse treatment of both the rebound and the rotation based on the full contact angle model. Contact mechanics model, what am I saying? So we talked about hot sphere and concluded that it had some limitations. The other approach is kind of doing the opposite. So the hot sphere model is to say, well, let's assume that the spheres are perfectly hard and they don't deform. The other approach is to say, well, maybe we should instead approach this problem from the opposite perspective. We made the sphere hard with the intent purpose of making the collision instantaneous so that we wouldn't have to resolve the very short timescale of the collision. Well, what if we were to make the sphere soft, highly deformable, like tennis balls? Well, if you do that, what's going to happen is that the collision will now take longer. A particle hitting a wall will deform and flatten and then bounce off. If you slow down this collision process to the point that you can now resolve it and on the fly in your CFD simulation, then you've also addressed the problem to some extent. So we'll talk about this, this idea. So in your course pack, there's the original paper introducing this idea due to Kundal and Strack was included. So those are the original people doing this. They were doing geomechanics. They were interested in modeling the mechanics of soil, okay, as in the form of a collection of interacting particles. So the idea is we're going to say our particles deform a lot, and as a result, we're going to essentially say a particle is like a mass, a spring, and a damper. And we're going to have our spring mass dashpot system represented using this set of equations. We'll have a spring constant K that will multiply the amount of deformation that's taken place. We can estimate this with looking at the overlap between, say, two particles. If I have particle A and particle B that are overlapping, I can compute their overlap, and this is what's sketched down here. So this is this quantity. Is that okay? So this is a amount of overlap between two particles. And I imagine I'm letting those two particles hit one another. I'm assuming that they can deform. Computationally, we're going to treat that as essentially particles being allowed to overlap a little bit. Once they let overlap a little bit, I can directly compute from basic geometry what is this amount of overlap, what is the overlap distance. And I can say that there's a spring acting on that. I'm going to give a K coefficient to this. Then, I need an orientation, so that's going to be along the direction of the AB normal. So the normal vector that joins the centroid of the two particles, A and B, colliding here. Okay, this is particle A colliding with particle B. We said we would introduce a dashpot, so I'll put an eta coefficient that will dissipate energy. A dashpot will just work with a coefficient proportional to the velocity of the relative displacement. So I'll have to compute a velocity vector that corresponds to the relative velocity between particle A and particle B. And I'll want only the normal, I'll put a little comma n here to signify that I'm going to be interested in only the normal projection to that velocity. So I'll want the relative velocity in along the axis of the collision. Okay. So this is along this collisional axis. I'm going to be interested in this relative velocity. All right. We're going to apply that if the particles are overlapping, meaning if compression has happened already. So if DAB, the distance between, well, sketched here as the two particle centers, if this distance is becoming less than the sum of the radii of both particles, then necessarily I have overlap. So if this is less than RA plus, whoops, RB, the radius of particle A plus the radius of particle B. no force. So now I don't have an impulse representation anymore. I have a time-resolved representation of the collisional force, of the contact force. And now all I need to do is integrate this. Okay, and this is the little contact model that I've introduced within this overlapping region. We can define a few things here. I introduced the relative velocity in the normal direction. So this normal relative velocity we can compute easily. It's a vector because we're going to look at the projection times the normal vector. So this is going to be UA minus UB, so the velocity of particle A minus velocity of particle B. We're going to project that onto the AB axis, and then we're going to remultiply that by the AB normal vector. Okay, so that gives me just the normal component. My spring stiffness is what I called K. This, we don't have to invent this. We can get this from Young's modulus. We know the material properties of our system. In particular, we know probably what is the material's Young modulus, which gives us an idea of the capability of deformation of our material. We have a damping coefficient. This damping coefficient that we called eta. Same thing, we don't have to invent it. We can solve this collision problem and figure out what is the ratio of the outgoing energy to the incoming energy, and solve for it analytically given this model. And what we find is that based on the mass of the particles, based on the damping coefficient, and based on the spring coefficient, based on the spring coefficient, damping coefficient, and the mass of the two particles, we'll obtain directly an effective restitution coefficient. Okay, so now if you assume that you know what the restitution coefficient should be, you can back calculate what the damping coefficient needs to be given the spring constant. So this is related to restitution coefficient. E, according to the following relation, which is just again obtained by just solving analytically this problem. This is a -2 log of E times the square root of MAB times K divided by pi squared plus log of E, the entire thing squared. The one thing that should make you wonder what's going on here is this MAB. MA is the mass of particle A, MB is the mass of particle B. MAB is, as you go through the solution process, it ends up showing up as the harmonic average between the two. So we end up seeing the effect of, or the need to define an effective mass being just defined by MAB inverse being equal to MA inverse plus, what am I writing here? I don't need a parenthesis. MA inverse plus MB inverse. Okay? So now, we're basically time resolving our collisions based on a reasonably simple model. What are the benefits? Well, now our collisions are based on a force. It's not based on an impulse. That means that if I want to do sustained contact, I just need my collision force to exactly compensate gravity. And then my sustained contact will be fine. So sustained contact is not a problem. If I want a particle that collides with another particle, This is fine. I'll have a force that repels one from the other. If I want a particle that collides with two other particles simultaneously, that's fine. I'll just have this force coming from two different collision pairs, or from two different partners in the same collision. If I want to have sustained contact and multiple collisions with many different shared pairs, so one particle colliding or touching 10 other particles, it's just going to be an additive treatment. Right? Every pair will lead to the same forces. So it is significantly more flexible. And sustained contact is fine. The story is not all good, and we can list a couple of negative points here. First of all, your particles are now assumed to overlap. Okay? For the force to be active, we need particles to overlap. Well, I don't know if you've ever played with sand, but it doesn't compress that well. Same thing with glass or any type of metal. So overlap, we know that it should theoretically be extremely small. So that's going to impact the cost of what we're doing here. So here, I guess the main point I want to make is overlap is a possibility, in fact, a necessity, which is not a particularly good model of the real physics. And collisions are going to need to be time resolved. Resolved in time. So let's talk about that and fix now a couple of things. The first thing that we need to fix is this. I don't know if any one of you know on the top of your head the Young's modulus for glass material or sand or metal particles, but it's going to be such that the true time scale of a deformable collision of any type of realistic particle material will be nanoseconds, if not much less. So hoping for the CFDE code to actually resolve that is kind of bogus. This is, in the first place, the reason why we started talking about Hauss sphere models. The collisions are so fast, so near instantaneous, that it makes sense to take them as being fully instantaneous. So this, we wish, but there's no way we're going to be able to do that. We're going to do what I would argue is the next best thing. For a number of years, researchers were saying, well, the real Young's modulus is this, but we'll take hundreds of it. We'll divide it by some number. We'll make our life easier. Well, really, there's a simpler, more pragmatic argument that one can make. And that argument is, as long as your collisions are significantly faster than all other resolved processes in your simulation, who cares how fast they are? There's no difference between a nanosecond and a femtosecond if your resolution timescale is, on the order of, say, your DT is 10 milliseconds. That's the argument we'll make. Small enough is good enough. So this is too large. The Young's modulus is too large, so the corresponding time step is too small. Too large, and therefore this is usually reduced to simplified time resolution. That's the first thing we fixed. Okay, and now, I think later in this document there's a couple of places where I show illustrations that this works okay. There's a second thing we need to fix, and that has to do with the first point that I made here. So, first of all, if we sacrifice the physical accuracy of the Young's modulus, then yes, collisions need to be resolved, but that's probably not that expensive now in terms of time resolution. Overlap is possible, well, that remains a problem. And we need to try to maybe not fix this because it's not fixable. By definition, we need a spring to act. So if we remove overlap, we cannot have a spring, but we can at least try to make this maybe look a little bit better. So the way we're going to do this is by recognizing that here there's a fundamental symmetry breaking issue. We're saying that collision should take place at the point of impact. Once there's particles touching, they should feel the collision. The way we're modeling it here is that once the particles touch and as they start overlapping, collision starts to kick in. Well, that's the drag term that I have a little bit above here. Not the drag, right? So that kicks in as soon as there's overlap. That means that we need overlap for this to happen. Well, what that means, let me hunt for a little bit of white space here, is that if I truly think about what the solution of that problem is going to be, think about this a little bit. Gravity pointing down, again, as it tends to do, and I'll put my particle again right here. Oops, no, I'll put it here. No, I'll put it here. Ah, why is it too large? What? Okay, I don't know how I did that. Well, and we're stuck with it. So let me do another particle next to it that this time hopefully will look good. So consider this problem again. With our model, can we truly do this? And I told you we can do this, and no one complained. Can I get a complaint now?
It's penetrating the wall.
It's penetrating the wall, right? If it doesn't penetrate the wall, by definition, there's no way I can have a collision force active. So I need to penetrate, I need for that particle to fall down through the wall enough that my repelling collision force exactly compensates mass of the particle times gravity. That means that there will always be overlap. Well, we can at the very least fix that by saying that the collision should happen maybe a little bit before there is contact. So we could create a region, some sort of a cushion region around the particle where the particle starts feeling the effects of this spring mass damper system so that a problem like that can be handled accurately. So the real solution so the real story is maybe a bit more complicated because really the amount of overlap needed to have a proper treatment of the collision depends on the problem. If I have the simple gravity problem, it's one thing, but now if I throw a particle at the wall, I'll need to start feeling the effect of the collision force sooner. Well, it turns out you can estimate that reasonably easily by looking at the collisional Stokes number. So you can simply look at what is the characteristic time scale at which the two particles or the two obstacles are approaching one another. And from that, you can back calculate what is a reasonable cushion region over which you expect that it would be probably safe to start colliding. So we're going to be colliding before contact a little bit. So we'll create this region of influence. Does that make sense to everyone why we're doing that? So we'll have around our particles, we'll be carrying around the region of influence to try to make this soft contact more symmetric. The good news is that this is incredibly simple to implement. And I don't know if any of you noticed, but I did not close my parentheses up here. And the reason is that I can simply add some sort of a cushion right up here. And that takes care of that. So now how I compute that is more of a modeling question. But in terms of technology, what do we need to put in? Well, we certainly need to add something to this or it will systematically be biased towards too much overlap. All right, so this is pretty much the entire story. Well, it's not the entire story, but it's a good fraction of the story. So this is what we're going to put in our code. You need more than that if you want to deal with particle rotation. So the next step here would be to include the particle rotation process. This is not particularly complicated to do if you do that in the same exact framework. So if we go back to this, we can treat our particle rotational dynamics in the same way with a spring mass damper system. Okay, so you can apply now in that direction as the particles rotate about one another the same system of equations. So this is what I write up here. That accounts for friction between particles. Now, there's a little bit more complexity here that needs to be accounted for. There always is a little bit more difficulties one way or another somewhere. So we argue that it's possible for a particle to slide, or it's possible for a particle to rotate. So we need to be able to transition from a model that accounts for the same type of spring damper dynamics to a model that gives us a simple Coulombic friction. Okay? So this is, sorry, yeah. So here, right? Here. The subscript is normal. The subscript here is T. After if. You're saying this should be N?
Yeah, I mean, is it N or is it not close to that? So, because how would we know? We are calculating based on FT equation, initially based on what?
It's telling
Oh,
estimated FT, but how we are comparing that.
right, but we're comparing against this, though. So this is the Coulombic friction law that we're comparing against. So we're basically saying that if the spring damper is less than the Coulomb friction law, this is what we should use. If not, we should cap this at the Coulomb friction law. Okay? So that it is still close. But I understand your question. If you didn't see that this is the same thing as this, then it's not obvious. So now we need to introduce new models. We need a tangential spring and we need a tangential damping coefficient. And so this hopefully is something that can be provided from experiments, or it can be estimated in some ways from knowledge about the material. We're not going to go too far in the details, especially because we're not going to talk more about that for our code today. I'll define the few things that I've introduced here. I have the tangential velocity between the particles. This is just my UAB, and since I've defined already the normal velocity, this is just this minus UAB comma normal. So I'm not gonna, I don't need to go much beyond. This is a full 3D collision, so we need to define the collision plane. This is not particularly difficult to do either. So our tangential vector, oh, I meant to say tangential velocity. And you need a tangential vector in which the collision is taking place. And that is just going to be given by normalizing your tangential relative velocity. So U, A, B, comma, T over the magnitude of U, A, B, comma, T. Okay, so we don't deal with this as a full 3D problem. the instantaneous calculation of the force is done in the 2D projection where the motion is taking place. And then there's this thing here, this delta t. Well, it's problematic. When you're looking at overlap like this, you can easily compute what that overlap is. It's directly is going to come out from the geometry. If I'm looking at overlap like this, right, two particles getting into one another like this, how do I know what is the amount of overlap that's happened? This is really something that requires knowing where we started the collision and time integrating what has happened to the particles as they rotate with respect to one another. So this tangential displacement is kind of a beast to deal with. And that complicates the story quite a bit. So I'll just make a note and we'll write what it is in 2D. I'll leave to your imagination / literature search what this represents in full 3D. But this tangential displacement delta t in 2D, this is really the time integral over the course of the collision of the tangential relative velocity. Okay, that's the simplest way we can know this information. So in 2D, I will compute this guy, which is then a vector, by integrating from the beginning of the collision to the end of the collision the relative velocity. So this is beginning of collision. And this is our current time. So that's tough. I don't know if that's obvious to everyone why it's tough to deal with this. So first of all, does it make sense that if I take two particles and I overlap them in their normal direction, right? If I bring them over on top of one another, I can directly from the relative position of their centers, I know directly how much overlap I have between them. But now if I think about two objects that are rotating against one another, the only way for me to know how much overlap or equivalent overlap has happened as they've rotated against one another is to time integrate the history of how much they've rolled on one another, which is what this operation does. In 3D, you have also to reproject systematically in the plane over which this is happening. So particles can be rotating and moving in 3D at the same time, so there's a bit more work to be done. Well, this now makes it kind of a deal breaker computationally. So far, everything we've done, we look at the relative position of the particles, we extract an instantaneous force, we're done. Here, we're saying, well, we also need to remember everything that's happened about a collision from the past. So not only do we need to know something about the current collision pair, but we need to know something about the time history of that collision pair. Well, the simplest way you can think about it is to say, well, that guy requires me to remember over time one parameter, one quantity regarding, oh, thank you. That thing needs to be remembered over the course of the time integration. What does it mean remembering? It means storing for the collision this one parameter. Well, how many collisions am I going to have per particle? Well, that's a tough question. So how much data, how much storage should I make available in order to keep track of that? Well, that's a tough question. Does it mean I need to start numbering my collisions? That's kind of a tough problem. So that really, really makes our life very complicated. Imagine if you have a pretty dispersed system. A tiny particle, I'm sorry, a large particle could be surrounded with easily hundreds of small collision partners. So that's potentially like 100 variables that you would need to keep track of for each particle you're storing. Remember, our particle so far has represented what? I, J, U, V, X, Y, and a stop, I think. Maybe one more thing, but we've been storing 5, 6, 7 variables. Now we're saying potentially you could add 10, 50, 100 variables and you wouldn't know a priori how many you need. So that's a big deal. I guess I'll just argue that this is expensive. Delta T needs to be stored over time for each collision, since collisions last for multiple time steps. So, since we've been talking about since we're interested in the computational aspect of things, I'll tell you what I'm doing for this. I'm not saying you should do that. But I saw this problem, and my conclusion was I can't possibly hope to run a simulation with 100 million intercolliding particles if I need to do this. I need to simplify that somehow. At the same time, I'm not convinced that the spring mass damper representation of the friction dynamics is that accurate. This tuning coefficients everywhere, it's not the most desirable. So a while ago, I asked my student Jessica Pisilatro, that was 6-7 years ago now, so 6 years ago. No, that was more than that. Actually, yeah, 7 years ago. To take a particle. Well, so first to dig out experiments. And we found this very nice experiment of people shooting particles with known incoming velocity at the known angle and known rotational conditions onto well-characterized surfaces and then measuring the outcome. So we had experimental data. And then I asked him to run the full model and look at the outcome of the collision. So we'll look at two examples here, and I have a third one, which is the tangential restitution. So this is the angle, the outgoing angle of the particle, okay? And this is as a function of the incoming angle of the particle. So depending on how you shoot the particle at the wall, how it bounces off. So this is something that is, not completely trivial, and the response is that you typically lose some angle, and you do that in a non-trivial way. The dashed line here, first of all, the symbols are the experiments. The dashed line shows what a well-fitted spring mass damper model in both normal and tangential direction behaves. You can see that it's beautifully capturing the rebound angle. And this is the same thing, and it's the same thing as a function of the incoming angle. This is now a measure of the rotational velocity, of the angular velocity of the particle after the collision. And again, the dashed line shows how you go through the experimental data points. Pretty decent. And then we started playing around, and we thought, well, it would be really nice if, in the most naive way, if we could simply say, that I don't want to compute. Let me simply never do that. Let me remove this if statement and simply use a Coulomb friction law. How much would we lose?
The simulations lines that a soft collision model.
And this is the answer. The black line here shows how much you lose if you simply use a Coulomb friction law. Now, in terms of computational implementation, if you're dealing with a small number of particles or rare collisions, that's fine. You can pay the price of the full tangential model. But this, to me, was a completely acceptable compromise for that then scales to much, much larger number of particles. Okay, so this is, I'll show you some use of those type of algorithms tomorrow, and this is systematically the assumption we'll be making. So I'll just say that cheap but decent simplification is to use only a Coulomb friction law. All right, and then we're essentially done with this. So we've spoken only about one particle, but obviously, again, this is an additive process. If I have multiple particles that are colliding with the same one, just keep adding. Basically, you loop over all particles that might be colliding with you, and you compute those forces, and you add them to your evolution equation for the in the Lagrangian solver. All right. Any questions on this?
This is published paper.
Yes. And you have, this is the Capicilatro paper. It's a small detail. It's a long paper, and this is a small detail in this long paper. Okay. There's many other, so it's included in your course pack, I think, for today. Oh, there's one more thing I wanted to add. Sorry. But it's very short. So I just want to say, so I told you, Young's modulus is all fine and good, but we can't possibly use the real value, so we're going to have to cheat. How do we cheat? Well, I can tell you concretely how we cheat. I don't want to hide anything. So I'll tell you exactly how we're going to cheat. So first of all, we need to deal with collisions between particles. There's inherently a CFL requirement associated with that. Now we're resolving the particles' trajectories, including how they bounce off one another. If you do not want to have overlap between particles, you cannot possibly let particles travel long distances, or else you will miss collisions. So there's a simple first CFL type of consideration that you should make. If I allow my particle to travel many times its diameter from t to t plus dt, if I allow this to happen, then I cannot possibly prevent that particle from at some point overlapping and potentially completely missing an interaction with another particle that might be static. So imagine this guy is static, and this guy is moving. What happened here is a missed collision. So inherently, if we say that we want to resolve the collisions, there's a CFL associated with that. So we'll introduce a new CFL. Well, I don't know, because I don't think we introduced already a CFL, but we'll introduce a CFL that will be exactly what you would introduce for a mesh, except we're going to say that it's now going to be tied to the particle diameter. So we're going to say that the time step size for your particle phase times some characteristic particle velocity divided by the particle diameter. This is a non-dimensional measure of how fast the particles are moving. A value of 1 means that the particle moves by 1 diameter in the time step. A value of 10 means 10 diameters in the time step. If I have a value of 10, I cannot possibly guarantee that 2 diameters down, maybe I had the particles and maybe I missed a collision with that particle. So this is going to be a problem. So what we're going to have to do, and that's where you might start realizing that collisions are tough, we're going to have to limit this with a small value. We're engineers. If you're not, what's wrong with you? But we want a small enough CFL. What is small enough? 0.1, okay? So we're going to allow our particles to only move a fraction of their diameter. That's the only way that we can guarantee that we will not overlook collisions. That's a big deal. That already shows that if one is committed to resolving collisions, the cost is going to be high.
What is delta dt?
And this delta Tp is going to be the time step size used for integrating the particle trajectory. Okay, so that's the time step used for the Lagrangian part of the solver. Right, the dxp over dt, so we've been solving the equation for dxp dt is equal to up, and we've been solving the up dt is equal to some coefficient over tau p times u fluid minus u particle plus gravity, etc., right? This was saying that we're doing an RK2 integration at time step delta Tp. That's what I'm saying. Yeah, so it can be kept independent from the flow time scale for sure. So we're not slowing down necessarily everything. Okay, so if I give myself a particle diameter, if I have a system that has some sort of characteristic velocity, which hopefully will be the case always, that tells me that my delta Tp is, at least from the perspective of collision, is going to be given, is going to be constrained. Or I should say constrained, not given. So it's constrained for the stable integration of these guys, but it's also constrained by this. And typically, except at really low Stokes numbers, this will by far dominate compared to the stability of the integration of this. Okay, so now we know more or less what is an unavoidable cost in terms of temporal resolution. Once we know this, we can figure out what is a reasonable stiffness that we can use for our problem. Let's get the most bang for the buck. Okay, so we accept that we're going to have to resolve tiny little displacements of the particles. How stiff can they therefore be? Well, you analytically solve your spring mass damper system problem, and you work out directly what is the amount of time spent undergoing a collision from the spring stiffness. What you find, so you can solve the collision equation analytically, and find that the characteristic time of the collision is directly related to, well, the usual suspects. The mass of the particles involved, the spring stiffness, and the restitution coefficient. So MAB over K, the spring stiffness, times pi squared plus log of E squared. Okay? What does it mean? Well, it means that I know that I cannot avoid constraining my time step size by this, but I also know that by tweaking K, I can obtain collisions as short or as long as I want. So really, that's what I'm going to do. I'm going to say that in order to resolve my collision, I should at least have 10 time steps across the collision. Okay, so I'll say it is reasonable to require delta T. I'm sorry, not delta T. We just call that T call or tau call. I will require tau collision to be at least 10 times my delta Tp. If I require this, I know that my collision will be properly resolved. And therefore, I can get directly, a priori, right? This is as you set up the simulation, you can get T-call from delta Tp, which you got from the CFL requirement. And from that, you plug this into T-call here, and you extract what K should be. This is let me write this down, this is not how you write the. This is the total collisional time. This is a time from first impact to final departure. This is the time it takes, okay? So if you have a spring K, a damper characterized by E, two particles of mass, of reduced mass MAB, the collision will take that amount of time. What did I write? Oh, collisional, yeah. I thought I had written something funny. We require this to be an order of magnitude larger than the delta TP. We know that delta TP has to require tiny displacement of the particles. Therefore, we can estimate T col. Therefore, I can work out what my K should be. So I know a priori, that's the upshot here. We've divorced ourselves from the true physics of the contact. We've essentially said those collisions are too fast for us to be able to resolve the true timescale of those collisions. However, I need to resolve the dynamics on the scale that involves tiny motion of the particles anyway. Let me make the problem as stiff as I can without making my problem more difficult to resolve. I'm already resolving at a particle CFL of 0.1. Let me make things the stiffest possible given this condition. Okay? That works fantastically well in a very general sense, but not always. I'll give you one example in which you might want to be careful. Well, in fact, we'll wait. We'll go back to that later. Wait, any questions on this? Does that make sense to everyone? So here, we're not even looking at what the material is. We don't even care. We're just saying this is the fastest collision we can deal with without killing a collision, killing any hope for CFD. But this should also guarantee collisions that are pretty much fast enough that everything will be resolved by the time a particle has moved by its own diameter, right? Particle moving by one diameter means we've accomplished T col. So collisions will be quick by all respects, much faster than everything else that were resolved on our flow solver. Any questions? Okay, so let's play with this for a bit. So we're going to take this. Oh, I need to. Yeah, let me unplug that. So we're going to go back to our original flow on the cylinder problem. And we're going to first deal with the collisions with the cylinder itself. Oh. Maybe. Okay. This code, so in the T4 directory 1_cylinder, that contains an almost perfect copy of the two-way coupled version of the LPT code from Tuesday. Okay, so the T2/2_LPT_2A. Almost perfect copy. I'll show you the differences. They're going to be very limited. What am I doing? If you look in here, I think the only difference is that I've reduced my integration time step size. Didn't want to hide that. We're now integrating at 10 to minus 2. I think before we were integrating almost 10, 20 times faster, I think. So we've significantly reduced the time step size. Okay? I think, I'm not certain, but I'm pretty sure that this is the only change in this main file. Then we go to LPT, where we're solving our particle equations. And there things have changed a bit more. We had already within a particle type the storage for collisions. So now you understand, now at least it should be clear why we have this. Each particle needs some place to store the sum over all the pairs of the collisions it's been involved in, basically. So it is, for drag, we don't need to do that. Is that big enough? No, it's probably too small. For drag, we don't need to store the drag force because it can be instantaneously computed from the knowledge of the local particle velocity, and the local fluid characteristics. So we can compute it on the fly. For collision, well, for a given pair, we can compute the collision force on the fly. That's fine. But then a particle could be colliding with particle 1, 2, and 3. And so we'll need to sum this up and keep track of that. That's why we need a storage space for the particle collisions. Working in 2D, we'll have a two-dimensional array for those collisions. I have a flag here that says use collision is equal to true, so I can turn on and off the collisions. I'm specifying, oh, so I should mention, I only included the normal collisions here. We are not looking at the rotation. So we have a normal restitution coefficient that I've set to 80%, 0.8. So an incoming particle will rebound with 80% of its energy. And then I'm, in fact, not even worrying about providing a value of K. Why am I not providing a value of K, the spring stiffness? Because we just showed that in the end, it only makes sense, or it makes the most sense to extract directly K from what I would ideally want the collision timescale to be. So I'm directly saying, well, give me a collision that lasts for that amount of time. How did I pick this time? Well, I just showed you on the other file my integration time. My integration time is 10 to minus 2. I'm now setting my collision time to 15 times that. This way, things are well resolved. I have no concern that there's many time steps in a collision. This amount of time is still less than, or at least on par, with the time scale that we were using for time integrating our equations on Tuesday. So this is the sacrifice that we've gone through here. We've slowed down everything in order to be able to maintain collisions as essentially the fastest thing going on in the system. Okay? This is an interesting trade-off. There's a cost again associated. Okay, so this is kind of it. There's not much else that needs to happen. Let me scroll down. Well, the collisions need to happen, so let's talk about that. The initialization is the same. All this is the same. There we go. There should be one change here in LPT step. LPT step is where I do two things. I add my particles on the left of my domain, And then I advance, I solve I integrate over time step size delta t all my coupled ODEs, and then I do some cleanup, remember. Well, here, I've added just that line. Account for collisions with soft sphere model. If you use collisions, we're going to do a step of collisions. So this is where I'm going to figure out the collision pairs, generate the forces from that. Then, once I've obtained those forces, what do I do with them? Well, it's kind of boring. The particle already knows those forces, it stores those forces, so I'm just adding them to the right-hand side of my particle equations. Okay? That's it. That's the end of the story. We have now our time integration done with our particle collisions. Remains to compute what this actually is. This is not a particularly complicated piece of code. There's some stuff I'm defining up here, but it's not necessarily a very straightforward thing either. There's a number of little tricks here. So the way this is set up is as follows. Again, remember, we're only colliding with the cylinder here. So for each particle, I'm going to look at whether it is in the process of penetrating inside the cylinder, and if so, I'm going to make it collide. I'll start by taking, for particle I1, my particle of interest right now, I'll set its collision force to 0, and I'll store the position of my particle, the velocity of my particle. I really wouldn't need to do that, but I had some code already ready. So I have the position of the particle, the velocity of the particle, the diameter of the particle, and the mass of the particle. Those are the parameters that come into the collision. And then I will collide the particle with walls. For that, I'm going to create a made-up particle positioned at the location of the cylinder. Okay, position 0, that has a velocity 0. I'm going to give it a 0 diameter because I'm going to need to come in and have some way of assessing whether the particle is penetrating, and I'm not going to rely on the diameter to do this. I'm going to do this down here. This is where I'm computing the overlap between my real particle and the cylinder. Okay, what is this? This is essentially the distance between the particle of the position of my particle and the center of my cylinder squared. So this is just the distance. Sorry, not squared. I take the square root. So this is purely the distance, and I'm looking at whether it is less than 0.5. My cylinder was of radius 0.5. I'm just looking at whether my center has gotten inside the cylinder. Nothing more. And then I need to look at, from that, the amount of overlap, because I thought it would be a bit unwieldy to do that in one pass. I'm saying that I will have overlap as soon as I am inside the cylinder by more than half of my own diameter. Right? The other way around. If I'm even outside, the cylinder by half of my own diameter, then I'm touching. Right? Because my particle has a size now. So 0.5 times d minus this quantity I just calculated. And then this r underscore influence is this radius of influence, this little cushion region that I have around, that I just provided here as a constant value. I don't want my code to blow up if a particle goes crazy and goes extremely deep inside the cylinder, which in that case would give me an enormous amount of overlap and therefore an enormous force, and that would just go crazy. I don't want this to happen, so I basically say, well, let's limit the amount of overlap. If there's too much overlap, something went wrong anyway, so please don't crash, essentially, is what I'm saying. So now, as soon as I have non-zero overlap, remember, this overlap here includes this radius of influence, so this overlap will start happening before true geometric overlap. Then I get to computing my model. What do I need? I need first to form a normal vector that joins the collision position and the centroid of my particle. Well, that's easy because my cylinder is centered on 0. So this is my n12, my normal vector between object 1 and object 2. I have some cleanup here that I could have removed. I really don't need that in this instance. So I'll continue down there. and I'll just compute the relative velocity. What is the relative velocity? Well, it's going to be right here. The dot product between, where is it? Oh, the relative velocity here is V1 minus V2. V1 was the velocity of my particle. V2 is set to 0. I take the dot product with the normal vector. That's now my relative velocity between the cylinder and my particle in the normal direction. So exactly the equations we wrote. On the fly, so here before we compute the M1 to this reduced mass, this effective mass, A may be that I wrote before. Restitution coefficient, K. I just gave you the equation for it. I know what my time-step size for the collision, not time-step size, but total collision time should be. I've specified what I want it to be. On the fly, I'm going to compute how stiff my spring needs to be to give me that net result. From that, K plus the knowledge of what restitution coefficient I want, I will directly generate the damper coefficient. And then I calculate explicitly the force, exactly the way we wrote. So minus K times the overlap in the normal direction, minus A dot times the relative velocity. That's it. And I increment that to my particle collision force. Not force, we've been working with acceleration, so I'm dividing by the mass of my particle so that I'm storing only an acceleration. This is it. This looks unwieldy, but this is just because there's a little bit of checks to make sure things don't go crazy. Any questions on that? No? Okay. So hopefully this runs. Oh yeah, go ahead. Yeah, let me show you again. So this is really those two lines. I understand that it's a bit hidden, and it is a bit hidden. There's got to be cleaner ways of writing that, but this ends up being a bit of copy pasting from my research code that sometimes is not necessarily the clearest. D12 is a distance, the same way we defined in our notes, is a distance between the centroids of the two objects that were colliding with one another. Okay? In that case, the centroid of object 1 is the centroid of a particle, R1, and that's the centroid of a particle, and R2 is the centroid of our cylinder, which is centered on 0 for our problem. So I take the dot product between the two and the square root, so that gives me that distance, and I subtract to that 0.5. What is 0.5? That's the radius of the cylinder. So if that value is more than 0, then I'm right outside the cylinder. If it's less than 0, I'm right inside the cylinder. But now we're talking about the centroid of my particle. The particle actually has a non-zero thickness. It has a radius. So this is why I'm accounting for that. I'm taking, in fact, 0.5 times the diameter of that particle, so the radius, and I subtract that to D12. So I'm basically looking at whether the distance from the centroid to the surface of the particle, the surface of the cylinder, is larger or not than the radius of the particle. That's essentially what this contains. And then I add this radius of influence, and then my question is this larger than 0 or not? If it is larger than 0, that means that my particle radius and the little cushion region of influence, all this is outside, there's no collision. If it's less than 0, either the region of influence or the radius I've gotten inside. Okay? Make sense? Okay, so that should run, hopefully. I'm hoping. So one thing you'll notice here, right away, is the CFL. The third column here was my fluid CFL. Because we've reduced the time step size in order to better resolve, to reduce the particle CFL, our fluid CFL has gone down as well. So we are over-resolving in time in order to allow ourselves to get collisions. Oh, I should have said, well, I don't know if I should have, yeah, so in order to provoke collisions, the Stokes number here is 10, okay? Tau p is 10, particles are little cannonballs, they should be going through. So let's see. So we should have our collisions. By the way, one thing that might be a good opportunity for us to talk about, my particle diameter here is 5 × 10⁻². Nsight can easily generate real particles, but it's a bit hidden. So if you're interested, you have to right-click on the measured/particle data, click on Edit, and then it's not available directly. You have to go to the top right here and click on Advanced. Once you're there on Advanced, you can scroll down a bit and you should be able to find a subsection called Node, Element, and Line. Okay? You click on this, it will expand this, this region. And that tells you there's a subsection, the subsection here that talks about the node representation. Right now, it's represented as a dot. We're going to represent that as a sphere instead. And then we can start asking ourselves what the size of the sphere should be. Well, the spheres we just said should be 0.05 in size. Hit Enter. And now you should have the true sizes of the particles as we are calculating them. You see, we have little balls. They're not colliding with one another still, therefore they overlap.
You can do it directly with the VS.
Okay, how?
Just highlight it and on the top bar, right?
Here?
Yeah, go to the right on the same bar. Few more. That is the node.
Oh, nice, thank you. All right, I learned something. I'm excited. So, not much to say. You can see our particles are clearly feeling the effect of the cylinder. We're not going through. Let me reload. This is so much easier. This is fantastic. Saving me an enormous amount of time here. We can color, let's color the particles by the x velocity. That should make pretty obvious what's going on here. So this should not be too surprising. The particles come in at the velocity of 1, which corresponds to color red here. The Stokes number of 10, we saw that this was still leading to particles getting a little bit entrained, at least a little bit feeling the effect of the vortices. So we still see that, no difference. What we were saying though is that the particles were getting inside pretty easily. They don't anymore. We see, in fact, no particle at all getting inside. The little particle you see at the very beginning, this is because Nsight, for at least, maybe not anymore, but a few years ago, if you asked it to visualize a field of 0 particles, it would very nicely crash. And so I got used to systematically putting 1 particle somewhere to accommodate the absence of particles. So this is this one little dot that shows up at the very beginning. Now, the particles are indeed bouncing off the front surface. And a particle hitting head-on the cylinder is going to bounce back. But then it will be re-entrained by the flow field. And therefore, it will not be able to penetrate back too far. And it will just start moving forward again and bounce on the cylinder again and again. Okay? So that explains this arc that we see forming here. Those are the particles that have hit the cylinder, bounced off, and ended up being re-entrained by the flow. Okay? Any surprise here? Any problem with this? Or does that correspond to your expectations? You can already kind of see that if you have an obstacle like this, there's going to be inherently a tendency to accumulate particles near the front of that obstacle. Right? The particles that are going to be bouncing back towards the left will be pretty natural collision candidates with the particle incoming from left to right. So you would expect that those particles here, the bluish particles, should be colliding with the red particles. Yes?
One more time, how to get this? I'm not getting.
You're not the visualization or the simulation? The visualization, okay. What I've done here is I've selected measured particles up here. So you click on that, and then what I've just discovered is that you go up here to the little triangular shape that's called node representation. Say it again. Somehow this was renamed. I don't know why. It doesn't really matter. But you can just still click here. And instead of using dots, you do spheres. You set their size, which is 0.05. Enter. Okay. If you want to remove the surrounding thing here, this looks a bit strange. You can remove that by clicking on this little thing. There you go. And then what I did is I colored this by the particle velocity, and specifically I chose the x velocity. There you go. All right. Other questions? Yep. Oh yeah, I don't know how long I made it run. It might still be running. I don't remember what I did. Let me check. It might be running for me as well, but yeah, I think I forgot to give it a reasonable exit condition. So yeah, feel free to kill it. Control C will kill the code for you. Though yeah, you've probably we don't need to run it any longer. If things look a little funky and there's a little shadows around individual objects, it's because of this little option down here, which messes up the look of this entire thing. This is a part highlighting button down here. So if you click on this, it will remove this highlighting and everything looks a lot nicer. Okay? Yes?
How does this Insight load the refresh data?
So Insight is not particularly good at loading new data that has been added. So the simplest thing to do is to simply reopen the file. You don't have to redo everything. You can save everything you've done in a sense and reapply the same thing. But basically Insight free is not going to let you do that too easily. So it would be easy, but in this case you might as well just redo everything. It automatically reloads data that you override though. Okay. Other questions? Okay, so this is just the wall. Let's get particles colliding with one another, okay? Except, is there another question? No. So, how are we going to do particles colliding with one another? We're going to take the chunk of code that we added, Gesundheit, and we're going to take it and apply it to collision pairs. Now, instead of looping over each particle and seeing whether it collides with our cylinder, well, the naive brute force implementation is to take each particle and apply this collision algorithm to each other particle. Okay? We look at whether each particle is colliding or not with each other particle. So this is the second code. So move to directory 2 called collisions. And I'll show you briefly how this looks again, because there's no significant change. But then for the third one, you'll do the work. Okay, so this is the same setup, at least I think it is. We're not removing the collision with the cylinder. We still want to be able to track collisions with the cylinder, okay? So this will remain. So if I scroll down to my collisions, this was my collision with, where is it? This is my collision with the cylinder, right here. Okay, so what am I doing? For each particle, I'm storing that particle's data. I'm basically renaming it. I wouldn't need to do that. And then I do my collision with a cylinder like we've just described. It's going too fast. There you go. This is the same chunk of code. So that takes care of collisions with the cylinder. But then comes the second step. I need to also check whether that particle is colliding with another particle. And so this is what I'm doing here. For each possible collision partner, which I identify by looping from 1 to the number of particles I have, I store also the information for that second particle, and then I go through the exact same algorithm, okay? In fact, this time it's even cleaner because it's not a wall, so I just compute the distance between the two centroids as the square root of the square of R1 minus R2. I set my radius of influence as a constant. I'm not worrying too much about this here. We could talk more about that, and there's more information in the paper that I've included in your course pack, but it's not the most important. Then half of the sum of the two diameters plus the radius of influence minus the distance between the two centroids is my amount of overlap. If that is more than 0, then I'm in the process of going through a collision, in which case I form my normal vector, my relative velocity, and then my reduced mass. I compute my spring constant on the fly. I compute my damping coefficient on this fly, and then I compute my force with the spring force here and the damping force. And then I add that divided by the mass of the particle to my collision storage. Right? It's an increment because I want to be able to deal with multiple collisions. Does that make sense for everyone? Is that it's the same algorithm, except now we're applying between all pairs of collisions, all pairs of particles. So let's see what that looks like. I'll let it run a little bit so that we have some data to look at. So the other run went up to a few thousand steps. Okay. So I've done 500 steps. Let me reopen Insight with my new data set. We noticed, by the way, when we look at the particle field in the previous case, that there was already quite a bit of overlap. Just from random distributions of particles, there were particles on top of one another. That shouldn't exist anymore. One of the consequences is that now there should be agitation in our particle suspension. So instead of having all the particles initially coming in at a velocity of 1, the particles are going to come in, but there's going to be some collision, so there's going to be some randomness in the velocity. And you can see that by the fact that, well, I guess you can't see that right here, but if I show this a bit better, you can see that by the fact that the particle velocity is no longer uniform. Okay? Before, initially, the front of particle was coming in straight with a uniform velocity. But now there's been collisions taking place from the very beginning. And so some particles have been ejected in front. Right? This guy's floating in front of the rest. And you see that the velocity is not the same everywhere. Well, collisions are starting to happen. We can also zoom in a bit and check that we don't have particles occupying the same space. So this is fundamentally what we mean by a soft sphere collision model. Okay? We are looking at soft spheres. They are legitimately able to interpenetrate a little bit. We can make the collision stiffer. If we want to make the collision stiffer, we probably have to integrate a bit slower, and then we would have less overlap. The question then becomes, what is an acceptable amount of overlap? By the way, this overlap doesn't change mass conservation. Okay? We're still, when we interact with the fluid phase, with the equations we talked about this morning, we still keep track of the sum of the volume of all the particles in the same way. Everything is done conservatively. But still, the physics of the collisions here are approximated in a way that is practical. But so you can see there's some limited overlap, but there is no fundamental issue with particles occupying the same space. What is the main thing you're observing with this code? I didn't really hear any. Computationally expensive. Yeah, it is really slow, right? It started off pretty fast, but it's been slowing down a lot. That's expected, right? Why is that? Number of particles, yes, but we don't have more particles than before, so what's the problem? Yeah, so the collisions, right? Exactly, and the collisions are handled right now by looking at each particle and checking whether it interacts with every other particle. We're brute forcing our way through this using a pure n-squared implementation of this problem. Okay? Each particle tests its potential collision with each other particle. You can deal with 10 particles fine, 100 particles fine, 1,000 particles fine, 10,000 you'll be done. So there's no real surprise in the behavior of all this. It's kind of a bummer that we end up in a situation where the performance is not particularly satisfactory.
Sir,
Yes?
sir, some particles are overlapping, just like they are making a roll like elements also.
You're saying particles overlap?
Yes, sir. This much overlap that they are floating like a roll element.
Yeah, right here, you're right, there's quite a bit of overlap.
Too much overlap.
Yeah, so we would need a little bit more, a little bit stiffer collisions. So probably reducing the time step size by another factor of 2, and the same way making the collision time scale less by another factor of 2. So yeah, this is suggesting indeed that we're not fully resolving this process here. So what are we seeing here? The particles are now bouncing on the cylinder. Before they were returning in the free stream and then getting re-entrained and forming this nice little arc. Now they can't do that because there's incoming particles. So they try to go back, but essentially they get, they bounce off the incoming particles, they get thrown onto the cylinder, and everything compresses right onto the cylinder. Okay, let us, so now I'll rest a bit, and I'll let you take this code and fix the cost. Make it fast, make it snappy. How do you do that? Our code for example number 1 was running fine. It took us a few minutes to have something that looked okay. Example number 2, we can't run. We haven't even been able to reach the outflow yet. Things are taking way too long, okay? So it's not an acceptable solution. We need to take our code and change something about it. We've already identified the main issue. The main issue is the fact that we have an n-squared treatment of the collisions. Can you fix that?
So we can find out number of particle levels.
Locally into the grid and only such like nearby, say 9 cells.
Okay? Does that make sense to everyone? So we don't need to collide with every other particle, right? We need to collide only with neighbors. What are neighbors? Well, the question, is this particle a neighbor, is fundamentally, again, an n-squared type question. That means each particle needs to ask itself whether it's a neighbor with every other particle. So is there a faster way for us to identify interparticle distance in a way that's maybe approximate but good enough? Okay, this is
The region of sphere. One particle center.
yeah.
The number of particles are in that region.
So, but how do you know whether the other particles are part of that sphere around you or not? So that's a very interesting idea, and that's probably one of, so the two people have said that now. That's a pretty standard methodology that would be successful. So that's one approach that you can use. That approach is to say, well, let me rely on some sort of a grid that represents my space. And I will decide whether that particle is in that grid or not. Okay? And from that information, you can simply now look, loop over the particles that are within your grid cell or the neighboring grid cells. Okay, so you're localizing your search to a neighboring region. And to do this, you're using the help of an underlying grid. Well, the good news for us is that we have an underlying grid. We have a CFD grid right here ready for us to use. It's not a completely obvious statement. We could have a grid that's utterly useless for this. We could have a grid that's too fine for us to use for this purpose, or too coarse for us to use for this purpose. So how would you go about doing that? Let me kill this because we're not ever going to get somewhere. So we're talking about using the underlying grid in order to help us identify who our likely neighbors are. So what are the tools you need for this? Oh, by the way, while we're looking at this case, you reproduce nicely compressible flow physics here. As far as the particle is concerned, this is a supersonic flow. Okay, the particle Mach number is larger than 1. Okay. So what you're forming here is literally a bow shock. Okay? Which is kind of cool. You can see very clearly, if you zoom in here, there is a jump in the particle concentration as you go from that region to that region. It's visible that there's a discontinuity. This is pure compressible flow physics. A compressible fluid works exactly the same way. It will form a bow shock in exactly the same way. So, at some point I need to get you to write some code, and I think we're now in front of us, so we can try that now. How would you go about adding a grid-based identification of neighbors? That's what I'd like you to think about and try to work on. Okay, and I'll be kind of moving around and see if you have questions or ideas on this. And then in, I don't know, 10, 15 minutes, we'll look at one solution, which is not the only solution, which is the one I've implemented. Don't cheat. Don't look at, where am I? Here, okay. So you seem to know what this is all about, right?
No, I haven't, but
Oh, you looked at the, yeah.
no, I didn't look at it also. I had this one. So
Yeah, we still have it.
my doubt is not still clear. So
Oh, okay.
initially we have to find this part, which is the tangential force collision.
Mm-hmm.
But this itself relies on tangential force collision, right? So is it like an iterative process? In your lecture notes, it was like this. So I.
Yeah, no, you're okay. I think I see what you're saying. Yeah, what did I mess up? Yeah, I think it is iterative in the following sense. You first write this as the spring mass damper solution, and then if it ends up giving you a solution that's less than that's larger than the Coulomb friction law, you limit it by the Coulomb friction law. Yeah, I think the if-else is not appropriate. It's not an if-else. Or let's say the if is not this, it's this really. Yeah, that's a good point.
So you said we are including soft model.
Yeah.
Okay. The soft model is young, some model is not that much high. If we say, because young model is a representation of the stiffness, the hardness of the
Yes.
particle.
Mm-hmm.
If the particle is stiffness high, so it will be chance that particle overlap will be less.
Mm-hmm.
To particle when the collision is there. Less overlap compared to soft particle of same material.
Wait. So I'm not sure I understood. So you're saying, yeah, we're using soft particles, yes?
These road elements are
Yeah.
creating here.
Yeah.
You are saying we have to this some DT reduce or something.
Yeah, so if we were to reduce our collision, the duration of our collision, because this is the way I parameterize this, or alternatively, the equivalent thing would be to increase the spring stiffness. Okay, that would lead to effectively a larger Young modulus, but that would require a shorter time integration. Yeah. So this, we probably don't need much stiffer, a much stiffer treatment. I didn't pay enough attention to what was going on downstream, but yeah, clearly we do need a somewhat stiffer system here. So we need to reduce the collision time, reduce the time to size a bit, and that would take care of this.
And so how much extent we can suppose we have some material that stiffness is young modulus 10⁹.
Mhm.
So to get faster result means to reduce cost. So how much extent we can reduce our young modulus?
Well, so this is the argument I was trying to make, that if you calculate the true collision time from or the collision time from the true Young modulus, you'll find in the densest region here. So this is clearly a case that's not that well parameterized. We would need to have, yeah, that's a lot of overlap. Looks like a cloud. So yeah, this is a case where we would need, it's not particularly complicated. We would need to go in here, and I have a collision time that's 15 times the integration time. It is probably reasonable for us to bring that down to 10 times. And then if we divide the collision, the interaction, if we further divide the integration time by 2 for the full code, I could bring that down to 5. So I could do this, and then similarly take the time step size up here and bring that to 0.5 10 to the minus 2. That should already give us a factor of 3 on the collisional time scale. So things should be quite a bit stiffer. So we're at time 2.
So you reduced the maximum and did you? What you did? What are the changes?
Oh, what I did was I went to, so I changed max dt and I reduced it by a factor of 2. And then I took the collision dt in the LPT.F90 code and I reduced that by a factor of 3. Why 3? Because I already had, so what I said in the notes previously was that I wanted to have about 10 times, the collision time be about 10 times the time step size. But I had it in the code as being 15 times the time step size. So I compressed that already down to 10 times the time step size. And then since we've reduced the integration time by a factor of 2, I reduced the other thing by a factor of 2. So that gives me a factor of 3. So we can take a look at this whenever it gets ready. The hope is that if I zoom in here, there should be way less overlap. There is still some overlap. Those two guys are not playing nice with one another, but this is also a tough problem. We're throwing buckets of sand at an obstacle here. This is, not the easiest problem to look at with an approach like that. Okay. Yeah, so you can see there's significantly less overlap. There's still some, but and also the other thing you have to see is that in 2D, we're playing here with a 2D situation, which is a bit conceptually it's a weird thing. Particles are not allowed to move in that many directions in 2D. You can get highly compacted particles. Or let's say you reach maximum compaction of an ensemble of particles very quickly in 2D, much faster than in 3D. Yes, things are Maybe not fixed, but they look okay now. And in the process, we have a nicer shock as well.
Suppose मैं इसको मैं ग्रीन का बुक चलाऊँ check आगे मेरा प्रॉब्लम मैं उसको उस ग्रीन नंबर ग्रीन नंबर मेरा आगे आई ओके
Okay, so anyone wants to suggest an algorithm for? Yes. Can you speak up a bit? Okay, so every iteration we update the location of the particle. The good news, we're doing that already. Yes.
At that time, we were finding the I and J for the particular cell.
Yeah.
Which cell the particle belongs to.
Yeah.
To dump basically the momentum source in that.
Yes.
At that time, we can put that particle ID as an attribute of the cell.
So each grid would have extra 2 pointers to all the particle IDs.
All right. Yeah. So now we're saying that the grid itself, so in the Eulean phase, we need to store information about which particle lies there. Yes, so we need to provide storage for that. In one way, a pointer would work, or a list would work, or something would, okay?
And then during the searching, we just search.
Okay. So the structure of the search will change. Instead of sitting at each particle and looping over all the other particles, we'll sit at the particle, figure out what its ij is, and then look in the neighboring region of ij's, and there interrogate a Eulean database saying, at that ij, what are the particles that I possess? So what do we need for this? Well, one way you can do this, if you want to avoid more complicated pointer-based structures, is to provide at each location information about how many particles are present in that cell. And second, provide an actual list of the indices of the particles present in that cell. Right? We're storing our particles in an array of particle structures, going from part on parenthesis 1 to part of NP. So we can easily store the index of the particle on our grid, and remember that. So we'll need an array of I and j for the position on our mesh, comma, the number of particles, from 1 to whatever number of particles we expect to have in a cell. Number of particles we expect to have in a cell, well, it depends how good or bad of a job we do at avoiding overlapping, first of all. If we allow particles to overlap, we can cram many, many particles in there. It depends, obviously, on the ratio of the cell size to the particle diameter. And it depends on the dimensionality of the problem. And then you probably want to have some sort of a safety factor there. So we're saying we need 2 arrays, and we need a small change to our looping structure. So let's take a look at this. Let me kill this. Oh, so that's the fairly poorly resolved collisions, and that's the significantly better resolved collisions. Okay? And again, you can still very much see the shock in this. Right, you can see this this bow shock here, right? Okay, so let's look at. Is everyone in agreement with this algorithm? Are there alternative solutions? And by the way, if they are, it's not impossible at all. It would be very interesting and potentially publishable. So. It's not a bad thing to have alternative ideas. Okay, so let's take a look at how this can work. If you move to the third directory, this thing will have only a modification LPT, if I remember correctly. We can take a look at it. Let me already, so I had here, I set it to 5, right? Let me do the same changes that I just did before. So this is now 0.5, okay. So, what are we going to do? We're going to give ourselves 2 new arrays, integer arrays. One will contain the number of particles lying in the cell. So I'm going to call that n part for number of particle in cell. Okay, so this is the number of particles lying in cells from cell 1 to cell nx in a 2D sense, so ij. And then I'm going to give myself, I'm going to delay the allocation of this here. I'm going to give myself an allocate table, so a pointer, if you will, that will give me, that will point to the list of particles that are existing at in that cell. Okay, this will be a 3-dimensional array. This will be I, this will be j, and this will be the number, the number of the particle in the cell. Okay, so from the first particle in the cell to whatever, the 10th particle in the cell. We'll initialize those guys somewhere here. So this is very much ad hoc. I am taking the ceiling of d over dp. Remember, d is the cell diameter, cell size. dp is the particle diameter. I am maxing it up to the closest integer. I am then squaring it. What is this? Well, this is an assumption of a nice little square lattice of particles. Okay, so I'm assuming that this is as many particles as I can have in my cell if they're nicely organized. I'm making sure that this number is at least 1. I don't want to mess up my array allocation. And then what am I doing here? Well, I'm basically saying this is wrong. Why is it wrong? Because particles will still overlap a little bit. And because a nice little lattice arrangement is not the closest packing I can have. I could cram more particles in the cell. I don't know exactly how wrong it is. I don't want to worry about it. I'm just going to put a factor of 3, and then I'm going to allocate this. Okay, so this is my storage for the information of which particles are lying at my cell ij. Now, I'm going to go through the collision algorithm. A fuse collision called LPT collision. Nothing else has changed here. Still the same code. And now I'm getting to collisions. I have a little extra chunk of stuff here. What do? I need to pre-sort my particles, exactly what we just talked about. Each particle already knows its own ij, so I can just loop through each particle. This is not an n squared problem, this is an n problem. For each particle, I simply get out its I and j, which I know already. I obtained it from my transport. And at that location, my counter for number of particles at that location, I simply increment by 1. Okay? I have one more particle that lies in cell iijj. And at that location, for an index that corresponds to my particle counter, I'm simply going to remember what is the index of that particle. Okay, so I remember which one of my particle lies at that specific cell. And I do that for all the particles. What I get out of that is a long sorted, basically my 1 to np indices are all going to be stored at various locations on my mesh, essentially. The rest of the collision proceeds exactly the same way as far as the collision with the cylinder is concerned. No change here, no need to change. But then we have the collision with the other particles. We started off with what I commented out here, what I call now a naive loop. This was the full n-squared treatment of the problem. We're replacing now this by a loop over my local mesh region. Again, I know already my I and j. Okay? The j is for my particle I sub 1 % j, and same thing for I. Well, I'm going to loop from one cell to the left to one cell to the right, one cell below to one cell above. So region of essentially 9 cells in the vicinity of my particle. And in that region, for every single particle that I've kept track, for as many particles I have in each of those cells, I'm going to get the index of the particle that exists in that cell. Okay, so the particle, I know which cell I'm sitting in. I'm going to look at each of my 9 closest cells, and at each of those cells, I'm going to say, okay, which particles do you have? Well, I'm going to have, say, 3 particles. Okay, for each of those 3 particles, give me the index, and then let's do the collision with that particle. Okay? We've just cut down this, the complexity of the problem enormously. Okay? This is still technically probably an n-squared type of treatment, except we have a prefactor that is scaling very close to n. So we've actually cut down the cost to almost linear. If we run that, and if I didn't lie too much, the main outcome should be that the code goes faster first, and second, that in addition to going faster, it doesn't slow down in any noticeable way as we start seeing whatever, 10,000 or 20,000 particles in our system. So remember, around 1,000 iterations, I think, things were really, really starting to slow down to a crawl. Does that make sense to everyone, what we've done here? So this technique doesn't come from particle laden flows. This is something that's been pretty standard for a good number of years from essentially molecular dynamic simulations, originating from an extensive body of literature coming from Professor Bird in particular, Boyd in particular. There's been an enormous amount of work there, where people deal with those objects. Those particles are not actual particles, but they are essentially surrogates for molecules. So they're actually solving fluid equations by keeping track of the molecules. They have no need for the underlying mesh, so they actually reintroduce the underlying mesh in order to speed up the collision process. Okay, you can see we've gone past this the 1,000 iterations, and we haven't slowed down in any noticeable way. The outcome should be the same. We've changed the algorithm, nothing else. So it's more of a sanity check that everything is still going all right. I'll let it go a little bit. So my plan for the rest of today is instead of ending a little bit early, I'd like to talk briefly about fluidization and particle beds. So now we'll go all the way, and we'll look at what happens if we start piling particles on top of one another. Okay, so we'll see that the method is amenable to dealing with what's people would, at least chemical engineers would refer to as the limit of the discrete element model. So you stop thinking about particle-in flows and start thinking about particle flows. The only thing that really matters is the particles. The fluid itself is a second thought. So the last series of examples that I had planned for the last day, but I think that we can go through pretty quickly since there's not a lot of very concrete manipulation. That involves saying what happens if I take an ensemble of particles and try to just pile them up under gravity, say. And then what happens if I start blowing it in, flowing within that ensemble of particles. Okay? So we're going to take a quick look at that and mention some of the things that are working, some of the exciting aspects, and some of the limitations. Let me reload that because I don't remember exactly what it looks like, and it's pretty cool. Oh yes, it's cool. So you'll notice that the very nice and well-defined structures in the particle distribution that were created in the first place by the interaction with the underlying vortices, as soon as you have a highly collisional flow and particles bouncing off one another and what we call granular temperature, so a certain level of agitation in the particle phase, as soon as you have this, this goes away. The system doesn't look, I would say, essentially at all. It doesn't look like what you would get from a nice series of uncommon vortices. And again, if you take a look at the velocity distribution, there's a high level of fluctuations in there. If I plot it from 0.5 to 1.5, you can see that particles are fluctuating in velocities all over the place. Any questions on this case specifically and what we've done with our collision treatment? Yes?
In the soft sphere collision model, you talked about molecular dynamics, right? So
Yeah.
is there any model that uses kind of like a model like Lennard-Jones potential, but the numerators are manipulated such that they can get better, less stiffer soft sphere collision model?
This is interesting. This question makes a lot of sense, and my guess is that there must be. In particular, I'm sure that people have looked at cohesive dynamics using Lennard-Jones type potentials. So I'm kind of answering the other way around. I'm saying there's probably been similar ideas used in order to model some effects in particle flows. Now your question is the other way around. Have those ideas of making softer dynamics been used in molecular dynamics, right? Well, I think this is already what typical molecular dynamics simulations do. They kind of work with bigger particles, representative particles that behave in a representative way. So this is kind of already, I think the answer is yes, although it's pretty far outside of my area of expertise. But most likely people have explored this, yes. Other questions? Okay, so let's make a bed. Except if you're not tired, then. Okay. Sorry. T5. Okay, so how are we going to make a bed? What is a bed? A bed is an ensemble of particles that are close packed that forms under the action of gravity, right? I'm just piling up sand at the bottom of a bucket. Oh, I can just do this. That will be easier. So I've changed the code here compared to what we had just before. So now we're going to keep the collisions, and we're going to do a few things. We're going to remove our cylinder. We're going to make use of our gravity vector. I don't think we've made use of it before. So now, I should look because I don't remember for sure. Our gravity is in minus x. So when we open things up in n-sites and our domain will look like this, gravity will be pointing to the left, okay? So our bed should be forming, packing to the left. We're going to place a wall for the particles only on the very left of our domain. So the particles are going to be experiencing essentially what you would call for a fluidized bed reactor, a distributor plate. So a system that allows fluid to go through but that prevents particles from coming out. I don't remember if we have walls, so we'll take a quick look at whether we have walls or not. So yeah, I'm putting walls. So I have no walls left or right. I have just walls on the side, okay? So this is essentially a column that's wall bounded on the sides, gravity pointing down. There's a system that prevents, so here in this case just boundary conditions, preventing particles from leaving from the bottom, but we will let fluid enter from the bottom and leave from the top. No flow here, but I think in addition to that, I believe that for this case, I turned off the flow solver altogether. So we're only simulating intercolliding particles here. What I'm going to do is I'm going to distribute a bunch of particles randomly in my computational domain and let the action of gravity force them to settle down, and the action of collisions prevent them from overlapping at the bottom. Okay? This is just showing you that we can capture a bed with this. Well, hopefully, again, I haven't run this in a while. This should run, and wow, it's fast. I probably didn't put that many particles. I can't remember. So everything is zero here because I'm not solving the flow field, okay? I have no flow field, I have nothing, so this is just the particles doing their thing. So let's take a look at what they're doing. Ah, isn't that beautiful? I should have looked at the size of the particle. Can you tell me what the particle size is? Because 0.05 still? Okay. Oh yeah, no, it might be different here. I'm not sure. Same? Okay, thank you. Yeah, that looks right. Okay. So now we're going to touch upon a number of cool things that we're really not going to talk about much, but I'll just point a few things out. So first of all, I should rotate this. So let me select here. So with a full 3-button mouse, you can easily perform the rotation. I want it to be exact, so I'll perform the rotation here. What? Please. The transformation editor down there. I'm going to choose rotation about axis Z, and this was not the right direction. This was, well, I messed up. There we go. So, the bed is not done, but what is happening? I have my random distribution of particles. They're falling down. They are not allowed to leave from the bottom because I have added a wall collision at the bottom. The same way we had this cylinder collision. But they fall. They can't really rebound because as they bounce up, they hit the particles that are coming down from the top. So they just kind of accumulate. By the way, I don't think I turned off drag. So what's going to happen is they'll also feel drag with the underlying flow field, which was set at 0 and we're not solving. So that's going to force them to remain quiet and not bounce around like crazy too much. So we're really in the process of forming a static bed. Is what you're saying here surprising in any way? So why do we see this shape here in the dense bed? Say it again.
For no penetration, this is the densely packed structure.
So in 2 dimensions, this is the most densely packed structure you can generate. This is not true in 3 dimensions. There is no such thing as a proper randomly packed bed structure in 3D. What did I say? In 2D. If I randomize a bunch of essentially cylinders, right, that's what we're dealing with here, and I try to range them randomly in 2D, all the same size, and try to pack them up, they will always end up having this so-called cubic face-centered arrangement. Okay? All arranged one in between the others. This is the highest concentration you can achieve. It is not random. The randomness comes from large-scale defects in the structure. It's kind of interesting. The randomness here comes from the fact that, well, we kind of didn't have a particle that was available to get stuck in there at the time when we compressed this. Well, this is random. That's life, by the way. This is, when you have a failure in any type of solids, metals. This is the type of thing that happens. You'll have either missing molecules, or you'll have the wrong type of molecule being inserted within a molecular crystalline structure. Okay, so what we formed here is literally a particle crystal. The reason why it's a particle crystal is because this is the most densely packed solution in 2D. If we were to go in 3D, those things can happen. You can have very nicely arranged structures, but those things in general will not happen because you are capable of compacting more particles in 3D in a fully random way than in a nicely organized way. So moving away from a lattice and going fully random in 3D will allow you to reach higher compaction. So this wouldn't show up in 3D. You probably have finished your bed. I don't know if I have, but I'll reopen mine and check. Yeah, it looks pretty much like a bed. Okay, so there we go. All right. So we've just formed a bucket of sand, something like this, right? So if you want to simulate a flow in a porous material, well, our Lagrangian particle tracking code has just allowed us to generate that porous material. If you want to look at a reaction process within a dense static bed of catalytic material, boom, this is what you get. I need to admit something though. It's not all perfect. It looks like a very nice bed. It is not truly a very nice bed. We're dealing with a representation of the interparticle collisions at all times. So basically every single particle is colliding with all the other particles, trying to find its proper position at all times. The result is that we always will see some level of agitation in the bed. A particle will move a bit, that will induce larger forces, it will be moved back, and we'll get waves of stresses developing within the bed. As a particle fall, it looks like they fall and they reach a steady state, but really, even after everything is established, there's still some remnants of bed stresses within the structure. And we're not looking at stresses here, we're looking at velocities. So this goes beyond stresses. Okay? So this is not a perfect method. It doesn't converge all the way to a solid mechanics perspective. I don't want to make you believe that either. So assuming that static is not what you as fluid dynamicists are interested in, you're probably still going to be okay. There's one other thing that I completely hid from you that I'm going to show now very bluntly. If I go back up here, no, not, yes, up here, that's fine. If I just look at the very top of the code here, the particle size is the same as before. What you'll notice though is that I have enormously shrunk my time step size. Why would I have to do this for the formation of a bed? But sure, but this is reducing this time step size would not really prevent the rebound dynamics. There's something that goes a little bit beyond here. Basically, I needed to make my collision stiffer, right? This is what I'm showing here. The restitution coefficient will not respond to that. So avoiding rebound is not really what I'm looking for here. Why would I need to make my collision stiffer?
There is no fluid flow.
There is no fluid flow, yes. But so what?
The collision, the coefficient, there is an restraining force that is obstructing the particles after it collides. So particles jump up with each other more rapidly.
Yeah, okay. It is. We already had pretty high Stokes number of particles, so the fluid was not softening the collision that much in the first place. It was a little bit. I think your argument is valid, and it would be even more valid if we had lower Stokes number of particles. But we had, I think, already a Stokes number on the order of 10 in the previous case. So there's one more reason that is much more stringent. So do we have, by any chance, a marker for the whiteboard? Alternatively, I could. You know what? No, don't bother. I think I can unplug and easily switch to this. It should take a second, like literally a second. Perfect. So let me go back to this for a second. So here I made this nice argument, like, you need to resolve, you need to make sure you don't move by more than 0.1 of your diameter. Oh, okay, the particles at the end are static, so they're not going to move by much. Their particle-based CFL is going to be 0. But, remember when I drew this, this picture? Of a particle sitting on top of the wall, subjected to gravity. Okay? We argued that we needed to do a few things, but basically, a collision force will essentially balance exactly the particle weight. Now, if I form a bed, that means I have a second particle on top of it, and a third, and a fourth, and a fifth. Let's look at the static force diagram for this. Each particle experiences its weight pushing down, the collision force with the particle below pushing up. That means that that particle feel that force, well, I should not go that fast. That particle feels that force, and then the collision force pushes back from the point of contact such that it exactly compensates. I realize that you're probably not seeing any of this. Okay? Now, what about the particle below? Well, the particle below feels the reaction to that collision with the particle above. It feels also its own weight, and therefore it needs to push on the particle below twice as much. The next particle feels this as well, and you can imagine that I'm pushing more and more and more to the point that the particle at the very bottom needs to be able to push against the wall with a force that is many times what you would have expected from a single particle. That means that if you don't want your entire bed to squish the bottom particles and have them overlap like crazy and penetrate the walls and all this, well, now there's a new condition on the stiffness of your system, and that condition is that your force, your collision force, should be larger and potentially sufficiently larger than the total mass of the vertical column above your particle, which is going to be, say, the particle diameter squared. That gives us a cross-sectional area. Then the height of the bed. That's now my volume times the density of the solid particle times the gravitational acceleration. And I don't need the... Okay, well, this here is the height of the bed. So now we're realizing that it's not that easy. You know, we essentially argued, well, hard spheres, etc., they're not going to be able to do this. Yeah, okay. It's not going to be easy for soft spheres either. In general, a Lagrangian method is going to have a tough time dealing with a very close packed system of sustained contact, of spheres that undergo sustained contact in a situation where you push on them in any way. So that's the reason why. So this criterion is what I used to generate my time step size, to then allow my collision time to be 10 times larger than that time step size, to then allow my resulting spring force to be sufficiently larger than this. That's the reason. Does that make sense? Okay, we'll just make one bed with the flow to just show you that there's no problem doing that in a coupled fashion, and then we'll blow from the bottom. So we'll kind of mimic a fluidized bed reactor for a second, and that's going to be our final particle-based use of this toy code that we've worked with. Can I unplug this? Good? All right. So let us form a quick bed, but this time with a flow. There should be no particular consequence, but I want you to see the effect of the two-way coupling. So the bed will respond to the fluid will respond to the dynamics of the bed. I think at least that's what I think the case is. Yes, coupled bed. Okay. I don't think I need to go through the source. It's a two-way coupled system. I'm just turning back on the flow solver. There's nothing more. As a result, it's going to be slower as well. Well, not that much. I think the mesh is coarse. It's 100 by 50 or something like this. So it's a cheap solver. So let's see, how long did it take to make the bed here? We got the bed in about 15 time units, which corresponds to, well, 15 time units. So let's see, we're at 2. So you can see things are going quite a bit slower. We don't need to wait too much, but let's see. We'll have a good idea what the bed looks like around 10. So this is not the most exciting case. I would just want to set the stage for this, to set the stage for the next thing, which is now showing that we can run simultaneously the two solvers. So this runs the two solvers simultaneously, but there's still no flow bound recognition imposed. So it's essentially 0 inflow, sidewalls, and 0 outflow system. So there's not going to be much happening. The third case we'll look at, now we'll have an injection of gas from the bottom. Okay. You guys are probably going a little bit faster than me here. Let me open it up. It should already show what I want to show, which is all right. We have our spheres. I think they're still the same size. Now, I will add, I had a factor of 10 in this. Okay, so it's been done for a while. I'll create a cut plane at k is equal to 1. There we go. So I have this plane to show the fluid behind. I didn't show the fluid before because we were not solving it, right? I'll just show the fluid velocity. I don't know exactly how large it should, or what is the range of parameters I should use, but I'll show it between 0 and 0.5. I'll plot it using a smooth velocity. There you go. So, particles fall. As they fall, they entrain the fluid down. As they entrain the fluid down, they start creating long wakes. It's a highly anisotropic flow that's being established, right? So we're kind of raking our fingers through this, if you think about it like that. We impart quite a bit of momentum in the flow. By hiding the particles, you can see that once we get to the bed, the particles are there, they're essentially static, they've fallen to the bottom. They essentially prevent much dynamics within the fluid. Now, if we wanted to approximate what's happening down there, well, I would be lying if I would be, well, let me say it and then I'll explain to you why it's a lie. If we had the full, let me put it like this, if we had the full equations we talked about this morning, including the volume fraction, essentially the equation we'd be solving inside the bed would be essentially Darcy's law, okay? So we have more of a porous flow model inside the bed. At the surface of the bed, however, the fluid is free to do its own thing. And its own thing in this case is, well, it deals with the induced fluid velocity. It's kind of funny how you can see the particles. I don't know if you can see this guy here. Look at that particle leaving this wake behind. Anyway. Our bed is more or less established. You can see that it has a bit more of a wiggly, it's not boom, it still moves a bit around because the flow has been made to fluctuate a bit, and as a result the particles at the surface are kind of oscillating left and right. Okay? And then we're left with essentially some sort of background flow in the box. This thing is done in 2D. In 2D, the only real solution is for this to form a large-scale vortex of some sort. So we'll have rotation in one direction, on the other direction, based on the original symmetry of our random distribution of particles. Okay? Everything falls. We establish some sort of a flow field, and we're left with some remnant background flow that will dissipate away. Any questions on that? That makes sense? Okay, keep in mind, again, this is where we've made a big approximation here. We did not include the volume fraction term that we derived this morning, right? This is close packed. The particles occupy most of the space in the grid cells. Therefore, our fluid equations need to be changed. Yes, it's two-way coupled. The particles are feeling the momentum that they're giving up to the fluid is feeling the momentum it gives to the particles. It's feeling its loss, but it should also feel the effect that it has less room to move. So we're not accounting for all the physics here. Last case, we'll attempt to perform fluidization. What is fluidization? Fluidization is the dynamical behavior of ensembles of dispersed solids that is observed once we have a fast enough flow that, in fact, the flow is capable of levitating the particle solid. So imagine I pour sand in the bucket, I start blowing from the bottom of the bucket. If I blow hard enough that the induced forces on the ensemble of the particles can compensate the entire weight of the bed, this bed will start floating around. It will, for a while, just behave like a high density fluid and kind of behave sluggishly. If you flow faster, it will start forming bubble, as if you had boiling liquid. If you go even faster, you start getting into fast fluidization, where the particles actually get entrained up, and they never really go back down to the bed. Okay? So we're going to stay far away from this regime of pneumatic transport. We're not trying to transport our bed to the top. We're just going to start to make it move a bit like a fluid. So the only thing I will do for this compared to the previous code, have I moved to the, yes. The only thing I'll do here is if I go to this demo flow, everything is the same except right here. Now, I have a directly boundary condition on the u velocity. I'm blowing in velocity 1. That's it. And if you want to play more with it, you can increase that and see how we go through the stages of the different kinds of fluidization. So let's take a look at how this looks. I'll give a few comments on that, and then that will conclude our particle-based fun on computers. And next week we'll have some interface-based fun on computers. So I don't remember at all how long I'm supposed to run this. So let me open it up and take a look. So again, this is the same case. We're blowing from the bottom now. Okay, so let's look at that first, and then I'll reload it in a little while. So, the paid version of Nsight allows you to not have to redo those things. You can save those actions and re-import them. It's more practical. But I can't really complain, so I'm not complaining. I'm not complaining. Okay, so this is this. Let's look at, again, let's create a cut plane. I'll place it at k is equal to 1. That places it right behind my particles, and I color it by the fluid velocity. So clearly, my fluid is blowing through. Let me change color palette. I don't want it to get confused with the particle color palette. But it's probably even worse. Let me just make my particles that's pretty good enough. Okay. So if we didn't have the particles, we have a uniform flow field here at the entrance going up. We have a wall here, a wall here. We should be looking at the Poiseuille flow. Okay? And indeed, we're forming boundary layers on the side of the walls. No surprise here. Then let's look a little bit at what's going on. The particles are falling in that rising fluid. Yeah, this is still very early on. There's not much happening here. You can see that the surface of the bed is more dynamic. There's more bouncing around, etc., etc. Oh wait, I can save the context. So let me save the context. And open. And restore the context. And select. Context. Okay. There we go. Can you see something happening here? You can see that the bed is slowly pumping up and down. Let me zoom in on the bed a bit. Oh, what happened? So if I zoom in a bit on the bed, you can start seeing waves of velocity. It takes a little while, but there you go. You can see that the height of the bed is oscillating. This thing is slowly starting to bubble. Okay, so the fluid needs to pass through. It will expand the bed a bit. This thing becomes unstable. The fluid finds place to pass through faster. And so we end up with this type of oscillating, bubbling bed dynamic. There's no clear bubble in this thing. And I also don't want to make you think that this is correct. This is, again, not correct. If we wanted to simulate a true bubbling bed, if we wanted to look at a true two-phase flow simulation where the fluid pushes cavities inside the ensemble of particles and navigates its way around and really fluidizes the bed, it would be absolutely imperative to include the effect of pressure. To properly include the effect of pressure, we would need to include the fact that the fluid doesn't have as much room to flow in the cells, and therefore some fraction of our cell volume is occupied by the particles. This is really important, and we're not really accounting for this effect at all because we're assuming that everything is constant density. So yes, we're getting the drag right, or as right as one could expect, especially considering that we haven't modified our drag law in order to account for the dependence of the drag on the volume fraction. That's another thing. But on top of that, we're not accounting for the particle volume fraction and the consequences it has on mass conservation as well as momentum conservation. Okay, and we're not going to do that again. This would blow up the code a little bit. This would increase its size a little bit. It wouldn't be complicated to do that. So I'll stop here. I'll show you that we can have some indication of bubbling, but this code is not at a point where we could truly look at the full process of fluidization. I'll show you simulations based on the same techniques, but including those things tomorrow morning. Okay? Any questions on this stuff? All right. If not, I thank you for your attention. I'll see you tomorrow morning.